We're going to look at a quick application of anti-reflective coatings. And this actually is now going to require us putting a few different ideas together from the chapter. So the first thing to recognize is that we need to talk about three different layers here. So there's air, i.e. what's outside of our glasses, there's then the coating itself, and there's glass. Each of these has a different index of refraction, n. There's the index of refraction of the air, of the coating, and of the glass. So make sure that you put a subscript on the end to make it clear which one you're talking about. Then we actually have a number of reflections happening in each boundary. And remember that if you're reflecting at a boundary where the speed would be slowing down, you actually get that phase shift. And we're in this specific situation, the reflections we're interested in, we do always get that phase shift of pi. So this is now a useful picture, thinking about our three layers, the air, the thin film, which is our coating, and then the glass. And the glass would probably keep going to the right. It's probably very thick compared to the thin film, but we're really just interested in what's happening at the boundaries. So notice that I'm looking between three different indices of refraction. N air is going to be 1, and for glass we can use 1.5. The film coating is going to be in between these. Depending on what type of plastic is used, what type of material it is, you would be given that in a problem, or you would be using the properties of it to find out what the index of refraction actually is. So we have two waves to think about. Remember, this is an interference problem, and so that needs to be the interference between two waves. And it's a little bit tricky because there's actually way more than two waves in the problem, but there's two that we're interested in. So there is an incident wave. That's relevant, but it's not specifically what we want to interfere. That first wave is going to reflect off the surface and some of it gets transmitted. Okay, that's cool. One of the waves we're interested in is then this one, that first reflected wave, from the air to the thin film. But then part of it's transmitted. This is not the second wave we want to worry about interfering. And notice that now that it is in a different material, it has a different wavelength. Now its frequency would be the same, and the reason its wavelength's changed is because it has a different index of refraction. The second wave that we're interested in is actually the wave that is formed from the reflection between the thin film and the glass. So the second wave we're interested in is going to be this one. But we're not actually interested in it when it's in the plastic. We're interested in it when it then leaves. So this wave can be transmitted. Now you might argue that a little bit of it gets reflected too. That's true, but that's not what we care about. So what we want to do is have destructive interference in the air so that you basically say that there's no overall reflection. There was in fact two reflections, one here and one there. But if those reflections destructively interfere with each other, it means that there's overall no reflection. One other thing that I want to note that's a little bit tricky in this problem is that we need to think about this distance and we need to think about this wavelength, but remember that that wavelength is going to change when it comes back out into the air. So always make sure when you're doing calculations like this that it's really clear to you and the person reading your work where you are actually talking about lengths and wavelengths. So this is again where it's really helpful to draw a picture and actually label the distances, label the wavelengths, so that when you do out the math, everything is consistent. So what does the math actually look like here? Well, we want a phase difference, and then we're going to constrain our phase difference to be the destructive case. But now notice that our normal equation has a lambda in it and a delta x. What is our delta x? It is the difference in distance that our waves travel. So one wave was reflecting here, but then our second wave went in and came back. So our delta x is going to be 2d, where d is this distance. So again, we have two waves, they're traveling a different path length, one went in and came back. This is again where it's really important to draw a picture so that you understand that it's not just d being the path length difference, but actually 2d. If you knew what the thickness of the glass was, that would have no impact on the problem because you're not worrying about anything traveling that distance. The next thing is that lambda. This isn't the wavelength outside in the air, it's the wavelength in the glass. Or sorry, in the thin film. Why is that? Because that's again how the wavelength it has when it is traveling this extra distance. So that's very relevant. That's what we want to think about here. That if we're talking about the distance in the thin film, we need to use the wavelength in the thin film. Then we have this difference in initial phase. That's maybe more confusing to think through. But remember, this incident wave from the outside was in fact the wave that started everything, right? So in a way we get to just argue that our phase difference is zero. It's a little more subtle because you do actually get that pi phase shift here, but you're also going to get a pi phase shift there. So you can think of this as actually two pi's canceling out. So what that looks like then is we put 2D on top, and then lambda over n is what that lambda is on the inside, right? So we have our lambda on the outside, we have the index of refraction in there, and so the wavelength on the inside is simply lambda over n. So when we rearrange, we get 2 times n times d on the top. So notice that this isn't second, this is 2 times n times d over lambda. And that's our phase difference between these waves on the outside. And again, the goal is to have them interfere, ideally destructively, or as destructively as possible. And so we then get this condition on lambda by saying that we want delta phi to be 2 pi m minus or plus 1/2, right? So in this case, you can say we normally start with 0 and then add 1/2, and here we're just starting with 1 and subtracting 1/2. So that's qualitatively the same. We're just changing where we start from, and we've made it a plus and a minus instead of a plus. But so that's how we've rearranged, that basically this phase difference and this term came on the bottom, 2 pi canceled with 2 pi, and so this tells us what wavelengths we get destructive interference from. So we can have lots of different incident wavelengths. Some of them we're going to have destructive interference on the reflections, and some of them we won't. So what that means is that anti-reflective coatings work for some wavelengths much better than others. And that's why with some modern glasses that have like new types of anti-reflective coatings, when you see the reflection, it actually looks like it's colored in certain ways. I think there's like one where you have green and another where it's purple. But other wavelengths, you're then getting destructive interference. And the book talks about this, that there's some additional subtleties here regarding the fact that they don't perfectly interfere just due to changes in amplitude, but this is still at least the idea. So this is a neat application where we can use destructive interference to have less glare, less reflection off the outside of your glasses.